In this short video, I will discuss what does random sampling in Monte Carlo means. Well, in physics, it sounds that Monte Carlo is random, but the physics that it simulates is deterministic. What do I mean by that? So, for a given model, that is for a particular radiation transport model or a model which is used to describe how protons are going to interact, we know the cross sections. And once we know the cross sections, we know how the particle will interact, which which interactions are going to happen, and we know the probability of that interaction. And once we had described the probability or given the probability distribution of a particular interaction in that model, the physics can choose the probabilities, and depending upon those probabilities an event will be simulated. So what is happening is we know the probability distributions of which interactions are going to happen. What we don't know is, in this Monte Carlo simulation, where that interaction is going to happen, when that interaction is going to happen, but we know how that interaction is going to happen because the probability distribution is known. That's what Monte Carlo is. It sounds random, but the physics that we are simulating is deterministic. We define the probabilities, and based on those probabilities, this interaction happens. Now, how this Monte Carlo picks a particular interaction or an event, how does that happen? So, uh, for starters, Monte Carlo does not sample dose, it samples events. For example, uh, from our probability, we will know from our cross section, we will know that the particle will travel this many length for this particular energy of protons, which will be quite random. And once we define a random number, we use that in Python, which is not completely random, but that's not the topic. Um, so free path length. Once a path length has been chosen, which is quite random, based on that path length, Monte Carlo picks one interaction type, which is also taken from the distribution which is given in that model. And from that interaction type, it will choose scattering angles, or if any secondary particles are getting produced. This will all be picked out from the distribution, and upon that the energy loss will be chosen based on these values. So the values that we are taking, depending on the path length value, which is random, we take the interaction type. For example, inelastic nuclear interaction happened. In inelastic nuclear interaction, the proton will be absorbed, and some maybe another proton neutron interaction can happen, and then the neutron will go out with certain angle. How that energy is deposited in the material gets uh, sampled. So it's not sampling the dose, it is sampling the events. From randomness to dose, if we track the history of just one proton, we'll not get what is actually happening. One single proton will not give us the entire picture of how, for example, the protons are going to interact in the patient's body, or are going to interact with the tumor cell. But a millions of protons will give us a pattern which is the average, and based on that average we can very accurately tell how the interaction is going to happen in the real world. Because we are now simulating it in the real world, we can exactly tell how the interaction is going to happen from this average values. So dose is energy deposited per unit mass, but we usually say dose is almost equivalent to energy. What happens in the simulation is each proton goes interacts, as I said before, interacts. Uh, for example, it goes elastic scattering. The proton will get scattered. One single proton will get scattered at certain angle, and it will go on about its business and then deposit energy in certain voxel. And millions of protons uh, will undergo random events based on the probability distribution, of course. And once all of them has been simulated, the dose will by that time the dose will have been accumulated in the voxels, and from that we can calculate the dose. So for one proton will have very little amount of energy which will not be useful to study or to get idea how the protons are behaving. But with a lot of protons the energy accumulates and we can tell what exactly is going on. And once we have a lot of protons interacting with the material, the the fluctuations in the proton's behavior, the extreme outcomes gets cancels out and it starts behaving what will be observed in the real world. That's the beauty of a Monte Carlo simulation. When we simulate a large number of particles, the fluctuations cancels out, and what we get is the real behavior. So the randomness disappears in the average, and that's how Monte Carlo uses random numbers, you can say, to calculate the dose. So now you know, people say Monte Carlo is random, but the physics that it simulates is deterministic.